Friends, welcome to my YouTube channel. Dhanesh here. We were discussing with transformers. Let's continue with the sessions. Most probably, I will be focusing on multi-head attention in this video. Let's continue. We will close this and we will start. Fine. Fine. It's fine. Transformers here. Yeah, in this video, my focus is multi-head attention and scale dot product attention models. They are the building blocks. In the last video, we discussed in detail about those scaled dot product attention models, but I'm covering here as well because that's the building block of transformers. Okay. Fine. You know these aspects. Even I discussed in the last video. Sequential data means order matters. Order is very important. Convoluted neural network. It's easy to parallelize, but the drawback is it cannot handle sequential data. When we come to RNN, it can process sequential data, but not able to parallelize as they are connected. Each one need the previous one's result. Fine, we discussed those aspects we discussed. See, transformers, it's introduced in 2017, and like LSTM, long short-term memory, transformers is an architecture for transforming one sequence into another one with the help of two parts, encoder and decoder. But it differs from the previously described existing sequence to sequence models because it does not imply any recurrent networks like GRUs, LSTMs. GRUs means gated recurrent unit. LSTMs means long short-term memory. These units use the recurrent neural network architecture, but our transformers, they don't use recurrent neural networks. Instead of that, they use attention models. Very important. This is the overall. It's a high-level architecture of a transformer. It contains a multi-head attention. Then it has the feed-forward network. It's a combination of multi-head attention plus feed-forward network. Now, what is this scaled dot product attention? The basic building blocks of the transformers are scaled dot product attention units. Transformer model learns three weight matrices. The attention function used by the transformer takes three inputs: Q query, K key, and V is the value. How you can to understand this, the query, key, and value concept come from retrieval systems. For example, when you type a query to search for some video on YouTube, the search engine will map your query against a set of keys, that is video title, description, etc., associated with the candidate videos in the database. Then present you the best matched videos, that is values. You understood that? Now, this is the architecture of the scaled dot product self-attention architecture. Here it's a high-level architecture. Here you have at t minus 1 and time t and t plus 1, query, key, and value are the inputs to the self-attention module, and you are getting the output from the self-attention module. This is a module wise what's happening. This is the inner story, what's happening inside the scaled dot product attention modules. See, first you have the query tensor and the key tensor. It's applied to a matmul, that is a matrix multiplication. So there it's the tensors, the query and the key are multiplied, then it is scaling down, then you are doing a mask operation, Then the softmax function, again, it's doing a matrix multiplication with the tensor value. That's what happening here in this diagram. So I will explain you what is happening in each module. The dot product of query and key. See, after feeding the query, key and value vector through a linear layer, the queries and keys undergo a dot product matrix multiplication to produce a score matrix. It's very important. It's known as score matrix. The score matrix determines how much focus should a word be put on other words. So each word will have a score that corresponds to other words in the time step. The higher the score, the more focus. This is how the queries are mapped to the keys. Next is scaling down the attention scores. How do you scale down the attention scores? The scores get scaled down by getting divided by the square root of the dimension of query and key. This is to allow for stable gradients, as multiplying values can have exploding effects. You may be familiar with the vanishing and exploding gradient in recurrent neural networks. Next is the softmax of scaled score. That's what we need to do in the next step. You take the softmax of scaled score to get the attention weights, which gives you probability values between 0 and 1. By doing a softmax, the higher scores get heightened and lower scores are depressed. This allows the model to be more confident about which words to attend to. This is the equation for the softmax function. You may be familiar with this. Next is multiply softmax output with value vector. So that's what we do in the next step, as in the architecture, as in the diagram. Then you take the attention weights and multiply it by your value tensor to get an output tensor. The higher softmax scores will keep the values of words the model learns is more important. The lower scores will drown out the irrelevant words. Then you feed the output of that into a linear layer to process. Next, we are going to discuss about the math of attention. As you know, Q, the matrix, that is the vector representation of the word in the sequence. Key, the K, the keys. V, the values. D suffix K, the dimension of the key vectors used, as we discussed. This is the math of attention. This is the important equation. This is what we discussed. You know, right? See, this is the vector multiplication of query and the key. Then you have divided it with the square root of the dk. Then you have taken the softmax. Then you are multiplying with the value. So this is like y is equal to w into x. Here x is the v and weight is this value. This is the weight. So you can see here, this is the weight. It's denoted by the weight. Softmax of q into kt, the whole divided by square root of d suffix k is the weight. Now, when we talk about multi-head attention, so we have discussed about the scaled dot product attention. Then why we need multi-head attention? See, this multi-head attention improves the performance of the attention layer in two ways. It expands the model's ability to focus on different positions. That is the first advantage. The second advantage, it gives the attention layer multiple representation subspaces. As we see, with multi-headed attention, we have not only one but multiple sets of queries, keys, values, weight matrices. uh, that is, the transformer uses 8 attention heads, so we end up with 8 sets for each encoder decoder. Each of these sets is randomly initialized. Then after training, each set is used to project the input embeddings into a different representation subspace. So that's why we use multi-head attention. To summarize, it expands the model's ability to focus on different positions, and it gives the attention layer multiple representation subspaces. These are all the advantages of multi-head attention. Then I will tell you, see, multi-head attention is just several attention layers stacked in parallel with different linear transformations of the same input. That's a multi-head attention layer. The multi-head attention layer, it contains one set of matrices like the weight matrix of the query, weight matrix of the key, and weight matrix of the value. These three, one set of the matrices of query, the weight matrices of queries, keys, and values, we call as an attention head. This one set we call an attention head. And each layer in a transformer model has multiple attention heads. Fine. This is the architecture. As you know, this is the scaled dot product attention module. Previously we discussed. Then we have the value, key, and the query. It passed to a linear layer, and after that it is passed to the linear dot product attention. Here you can see different layers are there. It's different layers. Finally their concatenation is happening and again passed to a linear layer. That's what we are doing. See, research has shown that many attention heads in transformers encode relevance relations that are transparent to humans. The multiple output for the multi-head attention layer are concatenated to pass into feed-forward neural network layers. See, that's all about the multiple attention head. Here we have covered most of the aspects. As you can see, you understood what is scaled dot product attention, you understood what is multi-head attention, and the architecture also we discussed both scaled dot product attention and multi-head attention. That's all about the attention models. Thanks for watching. Please like, share, and subscribe. Thanks a lot.